Welcome back to the Cerberus saga, everyone. This is a special episode. It is the final episode with the breadboard prototype, at least the final as far as my own planning is concerned. And the reason for that is that this is now complete. I've added the Z80 CPU in here. Here it is. And that was the final step. It's now fully integrated, fully rigged up. In the previous episode, I mentioned that I probably would not rig up the Z80 on the breadboard and wait for the first complete PCB prototype, custom PCB prototype. I've changed my mind because I found a way to make this breadboard prototype more stable. I was having some problem with parasitics, some spurious reads and writes, especially writes, but there was a fairly simple way to resolve that. What I've done, I have ended, using a logic AND gate, I've ended the read-write signal of the 6502 with the clock of the 6502, and that has the effect of shortening the length of the read-write signal, because every clock cycle, half of the clock cycle is high and then half of it is low. So because it goes low halfway through the clock cycle, it shortens the length of the read-write bus of the 6502. And that shortening of the length prevents spurious writes to places where it was not meant to write anything. Here's the change I'm talking about. I'm basically ending the read-write signal of the 6502, or the read-write bus of the 6502, with the clock for the 6502. By the way, this is a change. I'm now having a clock 6502 signal and a separate, let me show you down here, a separate clock Z80 signal. I separated the two clocks, so I clock only the CPU that is active at any one point in time, so the other one can go into a low power standby mode. Before I only had CPU clock for both CPUs, but that was not enough. So that's what you see here. I'm ending the clock of the 6502 with the read-write bus of the 6502, and that has the effect of shortening the duration of this signal here, since the clock is active for only half the cycle, and shortening the duration prevents these spurious writes elsewhere. The reason you see this inversion here is that this inversion is for the write, because the read-write bus is a write when it's low, so I invert it in order to get the equation for the write, and I don't invert it when I get the equation for the read, which is for the output enable. These are the read-writes for the video memory, read-write for the character memory, the write enable for the high memory, and the write enable for the low memory. All of them have the inversion because they're about writes. Only the memory output enable is a read, and then it's not inverted. And despite the parasitics, with that change the board became stable. So I figured, I can go ahead and rig up the Z80, because I can do the same trick on the Z80. It's actually cleaner on the Z80 because the Z80 uses the MREC output, or the memory request output, which is here. There is a pull-up resistor on it. And if you end the memory request output with the write and the read signals, which are here, both have a pull-up as well, they are active low. If you end the read and the write with the memory request, then you get a very clean signal, because the Z80 only activates the memory request pin once it has put an address in the address bus, and that address is stable in there. So the memory request only goes active or low when the address is already stable, and so ending the read-write with the memory request makes the memory accesses very stable on the Z80. You don't even need to end them with the clock, because the Z80 provides explicit functionality to achieve the same result. The Z80 has two signals, and there is a write signal, which is active low, and there is a read signal in a different pin, which is also active low. That's why the inversion, they are active low. And then I'm ending them not with the clock for the Z80, not with this,
The Z80 provides a signal that is specific for this functionality I'm trying to implement here, and that's the memory request, an output of the Z80 which becomes an input for spacer, and it's inverted because it's active low. So the write will only be applied to the memories after the memory request from the Z80 has been activated. In other words, after it has gone low. And this ending here, ending these two signals together, also prevents spurious writes. The rest is as you've seen before. Since we are here in the hardware description of spacer, which you are by now familiar with, I've made a couple of other changes. One I just mentioned. I have separated the clocks of the two CPUs. Now I have the clock 6502 and the clock of the Z80, so I can stop the clock of the CPU that's not active. There are a couple of changes in these equations here, which have to do with the CPU control logic, particularly this signal here, which plays a similar role to the ready signal in the 6502. So like in the 6502, when the ready signal is deactivated, the 6502 will halt, will stop executing. Buzz request has the same effect on the Z80, but the semantics is totally different. And that's why the logic that you see here is different. I don't use an AND, I use an OR. So I have two product terms instead of only one product term, as you see in the logic for all the other signals, even these ones here. And the reason is the following. I want to request the buzzes and halt the Z80 in all cases except one case, when the Z80 is selected and it's not halted by the CPU go signal. So the meaning of this is the following. When the CPU select is 0, that's why the inversion, then it's the 6502 that is being chosen. So this means the 6502 has been chosen. So in that case, or when the CPU go is 0, in both these cases, in one or the other, the buzz request should be active. In other words, we should halt the Z80. So you see, it's a different logic here, a different way of thinking about these signals than all the other equations above and below, because of the particular semantics of this buzz signal. This that you see here works. The final inverter here is because this is an active low signal, so we have to think in terms of activity, but then at the end we have to invert it because it's active low. That's basically it. These are the changes. The other change are the two separate clocks that we've already discussed.
So I rigged up the Z80. And I constructed a little built-in program to test it, and it's the same typewriter program that you saw for the 6502 with different assembly instructions. The Z80 has more powerful assembly instructions. The Z80 has a lot more instructions and more powerful instructions. It has a lot more internal registers as well. The 6502 basically has, I think, 3 internal registers. While the Z80 has 12, I think. Well, don't quote me on that. I have to look it up. I will put in the subtitles, or I'll put a message now on the screen telling what the correct answer is. But it's overall a more powerful processor with a more powerful instruction set. So it was actually easier to write a very short program to implement the typewriter functionality I've been using to test the CPUs.
So here we are back to the kernel code, which we've discussed over several episodes now. And in the last episode, we've discussed this function here all the way down called test CPU. And this is the function that gets executed when the user types out, well, test CPU on the command prompt. And it starts with an if statement. And last week we've discussed this first part here, which is when mode is 0, and that corresponds to the 6502. So it will test the 6502 by writing into memory a little assembly program in 6502 assembly, and then telling the 6502 to go and execute that program. And what gets inputted into memory are these bytes that you see here. And they are inputted in these addresses. This is the code area of the 6502. And these bytes basically correspond to the assembly program that you see in there. You know, the hexadecimal 0, then the hexadecimal CB, which is that one there, and then AD, which is C poked into memory, C for Cerberus poke in this line. So we are basically executing this assembly code here, which is the little typewriter application that exercises the entire control protocol between CAT and the 6502 CPU. So now we need something like that, but for when mode is 1, or for when mode is not 0, because that will correspond to the Z80. So this else statement here will put in memory a little assembly program that you see here, written in Z80 assembly, and it will then tell the Z80 to go execute that program. Now it's the same thing you saw before. The program is assembled into these bytes here, and this is what is poked into memory by the subsequent statements. The assembly itself is commented out. This double bar here means that it's a comment. It's just to document what these pokes are doing. They are putting this assembly code in memory. And this is the same application. It's a typewriter application, but the instructions are a little different. For instance, I'm using this powerful Z80 instruction, D, J, and Z, and what this basically does, it decrements a counter, compares that counter to 0, and then jumps if it's not 0. So you would need 3 6502 instructions to do the same thing. You would need an increment instead of the decrement, and then you would need a compare, and then you would need a conditional jump or a branch. And the Z80 accomplishes that in one instruction, which takes a couple of cycles to execute, but the instruction density is much superior to the 6502 because it has much more complex instructions. That's why, for instance, Sinclair managed to squeeze the entire kernel code plus a full-fledged basic interpreter in 8 kilobytes in the ZX81. That would not be possible with the 6502 code. Another peculiarity, if you live in 6502 land, you will notice that there are no stores here, and that is because there is no store instruction in Z80 assembly. The store is a load, but it's a load into a memory address. So for instance, this load here will load this value into register A, and that would be just like a load A in 6502 assembly. But this load here will load into the address pointed to by H1 or HL, and that value you see here. You load an immediate address into the register HL, and then the address pointed by HL will get loaded with the contents of register A. So this in fact is a store. It's a store A, STA instruction in 6502 assembly. It's just that the Z80 allows for many more addressing modes than the 6502. So you don't really need a specific opcode for stores. You can just use the load opcode with a specific address mode in which you are loading stuff into a memory address. That's basically it. So it's the same program that we did in the previous episode for the 6502. The result on the screen should be exactly the same. So let's see whether it does work as expected.
So when I turn the computer on, you are familiar now with the little starting jingle. It starts in 6502 mode. And we can do the same built-in tests I've explained in the previous episode. This tests the memory hierarchy, this tests the file system, make sure that it's reading files here from the SD card, in this case an image file. It allows you to peek the memory, so for instance this is address 2000, where for now I'm putting the code area for the 6502. The code area for the Z80, I'll change all this, I'll make it all consistent and uniform when I finalize the kernel code, but for now the code area for the Z80 starts from address 0 because that's the reset vector of the Z80, and right now you only see characters there because I just tested the memory, and when I test the memory it will put characters in the beginning of the low memory. And then we had the test CPU. Notice that it is in 6502 mode. You can see it here. So when I type test the CPU, it will test the 6502 with the Typewriter application that I've shown you last time. Very simple program of 8 assembly instructions. But now I can switch to the Z80 mode. So now we are in the Z80 mode, and I can also issue the test the CPU, but now it will run the Typewriter application in the Z80, not in the 6502, and that allows us to test all the communication protocol that I've explained in the previous episode. The same rationale applies to the Z80. So we go test the CPU, and it's exactly the same Typewriter application, of course with different assembly instructions, the assembly instructions for the Z80, but it's the same application, you know, it just works fine. And then we can go back to the 6502 and then test the 6502, and it works fine. The same application works just fine in both. So this shows that the CPUs are working. Something else I wanted to mention is particularly this resistor here. You see lots of pull-up resistors here on this side. These are all pull-up resistors. There are pull-up resistors here at the back, which you probably cannot see from this angle, but there are 2 pull-up resistors there. There is one more here, but it's this one here that I want to talk about. This is not a pull-up resistor. This is a drop-in resistor, and this cable here in green that you see here going down there, that's the RDY signal from spacer, the ready signal. And remember, when this signal is high and it's active high, the 6502 can proceed, but when this signal is pulled low, the 6502 will halt. It will just stop, because the rest of the system is not ready for it, so to say. In previous episode I talked about this signal. I showed you in the kernel code how we are using this signal, but I was using a normal pull-up resistor here, and that was a mistake, and the reason is the following. The modern 6502 or the W65CO2S has a instruction that the original ones from the 70s didn't have, and that's a wait for interrupt or WAI instruction. And what that instruction does, it basically halts the 6502 until it gets an interrupt. In this case, it gets an interrupt here via this cable, which is the non-maskable interrupt, which does have a pull-up resistor there. So until the interrupt comes, the processor, 6502, will do nothing once it encounters the WAI instruction, or wait for interrupt. The thing is, once it encounters that instruction, the way it will stop itself is by pulling the RDY signal down itself. It will halt itself by pulling down the RDY signal, which normally is an input, but then it sort of becomes an output because there is an internal pull down of that pin. And the system built around it has to allow the processor to pull down its own RDY signal, its own ready signal. So what I've done here to accommodate for this is, instead of putting a pull up, which keeps on forcing the signal high, and then in parallel with that, the RDY signal from spacer, that would create conflict, because now you have 2 parties trying to pull the signal up or down, and spacer may be trying to keep the signal high while the CPU is trying to pull it low to halt itself. So that's a conflict, and then you still have a pull-up that adds confusion to that. That's not the right way to approach it, especially because I am using the wait for interrupt instruction in the test CPU code, as you've seen in the previous episode. So the way to do that is to put a drop-in, an inline resistor. I am using 2.2 kilo ohm, and the RDY signal from spacer comes on one end, and then it goes through the resistor, and then it goes into the RDY pin of the 6502. So when they are pulling in different directions, when spacer is trying to pull up and the CPU is trying to pull down, the CPU will win, because spacer will encounter this drop-in resistor in line so it will lose the fight. So this drop-in resistor here has the role of allowing the CPU to pull its own RDY signal down, regardless of what spacer is trying to have it do. And this is important for the functionality. It was working the way I did it before, but when I looked at the signals in the oscilloscope, you could see that it was a tightrope fight going on there, and that was not good. But now it's working just fine. Even when spacer is keeping the signal high, when the 6502 encounters the wait for interrupt instruction, it pulls the signal down neatly, very neatly, regardless of spacer, and that's how it should be. Now, why are there so many pull-up resistors in the other control signals? Because many of these signals they're made for buses. For instance, the read-write signal of the 6502 is a bus signal. The read and the write signal of the Z80 are also bus signals. So is the memory request that I just talked about earlier in this episode. So in principle, they don't need the pull-ups and pull-downs, because say when the Z80 is not active, it will just tri-state the read and the write signals and the memory request. They will go into a high impedance state. So what is the issue? Now, they're made to work with buses. Well, the issue, as I explained in a previous episode, is that spacer here is a sort of control nexus. So I'm not using a control bus. I'm wiring all control signals into spacer. Whether they are inputs or outputs, they all go into spacer. And they go into logic equations, Boolean logic equations in spacer. And because of that, these signals cannot float, because otherwise the circuitry in spacer would not work. So when the CPUs tri-state some of the output control signals, such as read, write, and memory request, you need a pull-up to make that signal a logic 1. Because otherwise the equations here, the logic equations in spacer, will fail. Logic equations cannot have floating signals as input. Remember, and that's the important point, so I will repeat it. I am not using a control bus, and control signals that are tri-stated are made to be used in a bus. But I'm using a control nexus of full connectivity, so these signals cannot be allowed to float. That's why you see so many pull-up resistors in Cerberus. Because I'm not using a control bus, I'm using a control nexus in spacer, which gives me a lot more flexibility, even future flexibility, to change what's happening here, even after the final PCB is done. Because all signals are just wired into spacer, the magic occurs here. You already have all the traces going in and out anyway. So that's the reason I'm doing that, and that's the reason why you see so many pull-up resistors around the control pins of the two CPUs.
The only other change that merits some look is in the kernel code, the little Arduino sketch that runs on the Atmega and serves as kernel code. The change is somewhere here. Here it is. So this is the part of the code that determines what Cerberus should do when the user presses ESC or escape after the CPU has been set to run. Because once you go and execute a program in one of the CPUs, the 6502 or the Z80, the only way to come back to the normal Cerberus control window and interrupt that program is to press escape. So this is what the computer would do. If the CPU is running, when you have pressed escape, it will do this. Now, most of it you've seen before. You've seen this and you've seen this before. The addition now is that I'm pulling on the reset pin of the CPU. So I am resetting the CPU as soon as the user quits CPU mode and goes back to the normal Cerberus prompt. And the reason is that I found out, thanks to the breadboard prototype, that if I don't reset the CPU and I just stop it and go back to the normal mode, if I then switch to the other CPU, say I'm running the Z80, then I press escape, I stop the Z80, but then I don't reset it, and then I go and switch to the 6502 and run an application on the 6502, then there is some conflict, because if you don't reset it, the processor may keep a certain value in one of its control outputs that is not the default value, and that will get into the logic equations of CERBERUS, which is the control nexus, and it may screw things up. So I've realized it's important to reset the CPU once you quit executing a program on it, and then stop the CPU after it's already reached a proper default reset state. So that's what you see here. I have added the CPU reset being pulled high, and then we put the CPU in a high impedance state, and then we let the signal go low, and then just tell the rest of the kernel code that, okay, the CPU is no longer running, so we should clear the screen, print the frames again, update the status line, and clear the edit line. That's basically it. That's the only change.
And this completes the effort of building a breadboard prototype for CERBERUS. Next steps can be done in the PCB, and this gives me high confidence that the PCB prototype will work just fine. We will stress test it more, we will run entire applications on the CPUs, games and stuff, and that will probably allow us to discover things to change and optimize and do better, or bugs to correct, but that will happen in the first custom complete PCB. This breadboard prototype has done its work. I think I'll produce a special episode looking back at the history of this prototype, how it has grown over the weeks and months. Probably there will be no narration. I'll just put some images showing, like a time lapse of the growth of this prototype, maybe with some subtitling to explain what you're seeing. It will be a special episode after this one. I haven't done it yet. I don't know whether it will succeed, but that's the plan right now. And then we can retire this. I will not dismantle it. I will keep it for nostalgia purposes. I know 20 years from now I would like to look at it again if I live that long. But it has done what it was supposed to do.
So stay tuned for the next episode, especially now that you already know what it will be all about. And the episode after that, it will be about the design of the first complete custom PCB for CERBERUS. Take care in the meantime, and I will see you then.